Alright, so these are going to be our notes on gravity, and this is just continuing on the theme that we have of rotational motion. So we have rotation, or an object that's moving in a circular shape or motion, and it has a central axis. So this might be a person standing in the center, holding a string like a slingshot with an object on it, and he could be holding that, applying a centripetal force to it, and then it moves around in a circular motion. And happens a lot, like a Ferris wheel. You could be on a merry-go-round, and this kind of motion is caused by a centripetal force and gravity and other forces in the universe. But today we're going to talk about the idea of gravity. And gravity, which a lot of people don't understand, is a force that all objects possess. So if we were looking at this person here just by himself, so he's standing here, he has gravity. He has G. And also we have a planet, and these aren't to proportion. Let's just say we have Saturn. That has gravity. Even your pet hamster. Put a little thing, some legs on him. You have a pet hamster. He has gravity too. And something a lot of people don't understand. And it's an interaction between all objects in the universe. All objects have gravity, and all objects are interacting with each other. And it's a force that really, not that long ago, scientists didn't understand. If you have the sun in the middle, and you have like Mercury, you have Venus, you have Earth, then Mars, and then you have the asteroid belt with a bunch of asteroids out here, and then Jupiter, right? And Jupiter shouldn't be bigger than the sun, by the way, but just for this model. And for a long time they couldn't understand, well, what made these go in circles around the sun, right? And it wasn't until Newton and even Albert Einstein came along to really understand and explain how this works, and that it's a force that causes these objects to have rotational motion. And the axis is actually the sun. Okay, its gravitational pull on each one of these planets causes it to move in a circular motion. Okay, and we'll learn more about that later in the unit, but when we're thinking of gravity, the main thing we want to understand, or the thing that it depends on, is mass and distance. So you might say, well, how can a person have gravity? I've never seen anything stick to a person or be attracted to a person, but that's because gravity is very little. It's not very much. Okay, so the amount it has is just overridden by the fact that this person's on the Earth, and that gravity is so much greater that it overtakes the gravity a person would have and causes that object, if it was like a rock, would cause it not to be attracted to the person, but to just fall to the ground. The gravity of the Earth is so much greater because the mass of the Earth is so much greater. And then also, an important thing to remember about gravity as well is distance. Okay, and how far apart two objects are. So when we're calculating, gravity of the sun, you start saying from the Earth, out to here, the distance is 93 million miles. That's a big distance. But the gravity of the sun is so great, because the sun is so massive, that it still affects the Earth. And even the Earth, you figure out about how far away the moon is. It's really far. But it's still, because the Earth is so massive, it still has a gravitational effect on the moon and other things around it, even a satellite and those kind of things. the equation we use, and also I just want to say before I move on, is we always want to calculate this distance as a radius, because really we're doing a circle, right? So if we were doing, let me color code this in, say green. So the sun right here, this is the radius of the sun, and we were doing the earth, say the center of the earth, and this is a circle, right? So that's what makes it the radius. It's halfway across, right? And if you measured across here, it'd be the diameter. Okay, and planets actually have ellipses, and that has something to do with just the great distance that exists between the Earth and the Sun. And we sometimes think of these planets as having these circular orbits, and for the most part, if we looked at them, they probably would be. And oftentimes we exaggerate them when we draw them as ellipses, just to show that they're pretty close to being circles, but in the end they're not quite circles, so they're ellipses. And it has to do with, being a little bit closer on one side, a little farther on the other, and kind of stretches that out a little bit into an ellipse instead of a circle. But that's how we do the radius, from the center of the sun to the Earth, and then that would be our radius, or the distance. So the equation we use, force of gravity, is g, which is this constant that somebody actually figured out, a scientist. We take that constant, we times it by the mass of one of the objects, times the mass of the second object, and then the distance between the masses squared. So this might be the sun, mass 1, this might be the Earth, mass 2. And then we just divide that by the distance between them, squared. And then also multiply this gravitational constant as well. Okay, and this is all related to centripetal force, because the sun is pulling on this Earth, due to its gravitational force, but also the Earth is kind of moving this direction, so it has this tangential speed. So as it moves it, it kind of causes it instead to have this circular pattern, because the sun is constantly pulling on it as it goes around, but the Earth is constantly moving out this way, and it just keeps it in this circular path around the sun. And the constant is equal to 6.673 times 10 to the 11th. It's a big number, and so keep that in mind. And it's actually negative 11th here. Keep that in mind, negative 11th. And the amazing part of this is this gravity can be seen. We can actually see it taking place between the sun and the moon, or the sun and the Earth, or even the Earth and the moon is actually what we're seeing. But an example of the effect gravity can have is the Earth and the moon. So let me cancel some of this stuff here. And let's see. So if we have the Earth and the moon, a little bit closer, we'll go darker for these guys. So the moon. And there's gravity. So the Earth pulls the moon, but the moon also does the opposite as well. It pulls the Earth and has gravity on it. But the Earth is made up of different substances. Most of the Earth is made up of, the crust. But on top of the crust is water. And water has the ability to flow different directions. And as the Earth is also spinning, let's draw that in there. Go some pink. So this Earth is spinning. Okay. And part of this water, we'll draw some water in there, just so you get the one a little bit thicker. So you get this water on the outside surfaces, right, of the Earth, and then to whatever side that is facing the moon, this water tends to be pulled to that side. Okay, so the moon pulls it, and as the Earth rotates around, or the moon, rotates around the Earth, then, because this is happening like this, the Earth is spinning, other things, the moon's spinning, same speed actually, and then the Earth is going around the sun as well at the same time. So all these interactions are taking place, but the gravity of the moon actually pulls this stuff, the water, towards it, and changes, makes the level of the water go up and down in certain places as the Earth moves and the moon rotates around it. And that's really what causes tides. And we'll probably go into this a little more in class. So let me just keep going. And also, as I said before, gravity causes slightly elliptical. So if we were going to say the sun is like this, we'll draw the Earth much smaller, and then really the orbit is more like this. Okay, so, and that's exaggerated, and these have these foci right here. These are all the same distances, and this is really the more accurate, but these are great distances. So when you would think this is really this oblong shape, it's not quite really oblong, but it is really more a true reflection of the orbit of the planets around the sun. And what's also important to remember about gravity, it helps determine weight. So each person, when they go to the doctor, they get their weight determined, and really what they're getting is their mass times their gravity, because we have weight because the Earth is pulling on us. It's a force that's pulling on us. So we're on the Earth, right? There's a person standing there. Okay, and when we're doing that, the Earth pulls with a certain force on us, and we can figure out what that is, our weight, if we just take the acceleration due to gravity, 9.81, and we times that by whatever our mass is. Okay. So that's something to keep in mind. So whenever you're going to the doctor and you're standing on a scale, you get the little scale. Let's see if I can draw something remotely like it. Okay, then you stand on it. Some of us like to go to the doctor and such because we get our height measured, right? And we think, oh, we're really tall or whatever. But also they measure the weight, and really what they're measuring is the force of the Earth and how it's pulling down on us, and that's just our mass, how much we have, times acceleration due to gravity, which is 9.81 meters per second. And then we could say it's in newtons because it's a force. Okay, so that's our notes on gravity. We're going to look at this a little bit, do some calculations on it, talk a little bit more about how these things are related, and these are usually the hardest calculations. There's some big numbers when you start looking at the mass of the Earth and Saturn and the Sun. So just keep that in mind. Hopefully you know how to use exponents on your calculator, and make sure you annotate these and show them to me.